Hello, welcome back to the video lecture series for Introduction to Data Programming using Scala. In this video we continue looking at our mutable singly linked list. In the last video we wrote several of the methods for it. Now we want to finish that out. We have three more methods that we want to write. An insert, an iterator, and a remove. Let's start with the remove. Mainly because as my way, I generally go from easiest to hardest, and I'm going to argue that insert all is probably the hardest, but remove is definitely the easiest of these. So when I want to remove a node, if we look at our picture, let's say I wanted to remove this node here. This is node number 2. So what I would have to do is I would have to walk. Now note that I don't want to walk 0, 1, 2, because if I get here, I've gone too far. Turns out when you're removing, you need the node before the one that you're going to remove, because you have to reset this pointer. In order to take this node out, what I really need to do is just direct that pointer over to here. And actually I can leave it just like that. It doesn't matter that this has a pointer going there. This is a one-way connection. The rest of the linked list doesn't know about it. This node will then be picked up by the garbage collector at a later date. Okay. So all I have to do is find the node before the one I want to remove and then change its next pointer. Okay, so let's see how we can put that into code. And note this is also supposed to return to us the data of the thing at the node that we are removing. Okay, so I'm actually willing to start off by copying the apply method and then figuring out what changes need to be made. So removing, they asked for something that's out of bounds. Otherwise, Rover equals head. And now this has to stop one shy. Okay, I can't go all the way up to the node that contains what I want to remove. I have to stop one before it. And that in and of itself might indicate another special case that I need to have in here, but we'll continue on with this as it is. So I walk until I get to the node before the one that I want to remove. At this point, I need to remember the element, the data of the element after the rover. So data or rover.next is the thing that we are removing, and so rover.next.data is the data that's being stored there. And then to actually do the removal, we do rover.next equal rover.next.next. Okay, now these types of expressions here where you have multiple dots in them, they often wind up confusing students, so let's talk about what this means. So once again, if I was removing this element, we stop, so I said I'm removing element 2, our loop would go 0, 1, and it would stop there. So Rover would be pointing at this node here, and I need to pull off the data from here. So since this is Rover, Rover's next is here, and I pull off the data element. So Rover's next data gives me the data that I want. And then I want to set Rover's next, so this pointer right here, and I want to set it to point to the box down here. Well, where do I have a box for this? Well, in the next pointer of Rover's next. So I set Rover's next equal to Rover's next next, which makes this pointer here point to the same thing that that pointer there does. And so that's what we put inside of the code there. Now, this works for most cases. It works very nicely for the case that I was illustrating here. It does not work for all cases. There's also another shortcoming here. In general, you might have noticed that the shortcomings that we tend to have for this are when the things that we are modifying involve the head or the tail. What if the element that I was removing was not this one here? What if the element I had been removing was this one here? Well, then the rover would stop here, and it would take this pointer and set it to Rover's next next, which would be null. And so it would blank that out, and everything's happy, oh, except for the fact that the tail is still pointing to this node, which is no longer part of the list. So we need to do one check there. When we're done with this, we need to say if Rover's next is null, then TL equals Rover. Okay, because we removed the last thing, and we need to, the thing that we were pointing at, our rover, is now last, because we've taken out the only thing that was after it. Okay, what about the other end of the list? So one extreme case is when we remove the thing at the tail. What if we're removing the thing at the head? Well, in that case, we don't need to walk our list at all. All we need to do is take the head pointer and point it past to that next element. Okay, so let's go ahead and edit the code so that we have this special case here. If the index that I'm removing is equal to 0, else do all this other stuff that we've written. Okay, well, in this case, the thing that I am removing is head. So let's make our return variable that we can return it there. And I want to link around that first element. Okay. Turns out that for this case as well, what if our list only had one element in it and we remove that one element? Well, then it's possible. So if we did that, then HD would be null. And if HD is null when we're done with this, I should set TL to null as well. That would be the case where I have one node, head points to it, tail points to it, and then we remove it. Okay, well, in that case, the head should be null and the tail should be null. Another thing that I need to do inside of here, either way we go in this, num_elms minus equals 1. And because we have just taken something off of our list. Okay, 2 more items to write in here. I'm actually going to go with iterator first. Because it's, I don't know, I think it's a little bit easier. The main thing is that we need to be returning an iterator. And that's really where the challenge comes in here. So what does an iterator need to have inside of it? Well, the iterators in Scala have a next and a has next in them. So we need to def next. And next returns the next element, so it's type A. And we also need to have a has next, which returns a Boolean. So the thing about iterators, we've seen that when we want to walk through a linked list, we wind up using this scheme where we have a rover. We have some type of variable and then a loop, and it takes that variable and sets it to the next. And so that's how we walk through a linked list. The purpose of iterators is so that you can walk through a linked list or an array or whatever and do it all in the same manner. So it doesn't matter if you're walking through a linked list or through an array or some completely different data structure. If they can give you an iterator, that iterator has the job of making it so that next and has next do what they're supposed to do, so that someone can write a simple loop and have it work. So how do we make this work? Well, it turns out that we need these to do exactly what our a for loop or a while loop would do. This is more of a while loop here because the has next is giving us back a Boolean, so we want to say while iterator dot or iter dot has next, then we pull off the next. Okay. Just like this, probably the best way to do this is to make a rover and set it equal to the head. So how do we know if you have next? Well, rover's not null, there's another element in the list. I'm going to go ahead and take out that white space. What about for next? Okay, if I want the next element in there, well, first I need to give them the element at the current node. So I get Rover's data, and I return at the end, and then I set Rover equal to Rover.next. And this gives us a proper iterator for our linked list. So if you picture this being inside of a while loop, the while loop asks, is Rover null? If Rover's not null, it pulls off the data from the current Rover and moves Rover to the next value. And then it checks, is Rover null? And pull data, move to the next. Boom, 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 boom. Over and over and over again. And so this iterator will allow you to walk through a list even if you know nothing about its internal structure. In fact, because we made our node class private, nothing outside of this list can walk through nodes. But we've encapsulated that inside of here so that outside code doesn't have to know about the nodes. It doesn't actually have to be able to make a rover, and it can walk through it in an efficient way. By the way, never walk through a linked list using apply. Okay. Why not? Because apply has a loop inside of here. So when you do apply 0, this is really fast. But then apply 1 takes a little longer, and apply 2 takes a little longer, and apply 3 takes a little bit longer than that. And so if you have n elements in your list and you walk through all of them with apply, you wind up doing n squared work. Okay, so you never walk through a linked list by repeatedly calling apply. You instead use an iterator, because the iterator has this rover which keeps track of where you are. Okay, our last method here is insert all. Just by writing that, I'm getting rid of our one error that we had. Yay, everything is happy. Obviously this won't pass the test on insertion. So the insert all is somewhat more powerful than for example, remove. Removed a single element. This is a little bit more complex because it potentially inserts multiple elements into our list here. Maybe it's just one element, but we don't know that a priori. So, the first thing we need to do is, just like with all of our other methods, well, first I'm going to do something that looks like that. Except I do believe that we can insert at the very end, so I'm only going to throw the exception if we actually go greater than num elements. Then I'm going to create a rover, and just like with remove, I'm going to walk one shy. Okay. So this gives me the node before where I want to do my inserting. So let's go back to our picture here. And let's say that, so I've obviously drawn some things in where we insert into the middle. What if I was inserting several things into the middle? Well, that makes it just a little bit harder, in that I need to do this process across a loop that runs through the elements. Okay. But the whole process of adding stuff, once again, if I want to add at the index that's equal to this node, I don't want to walk all the way to this node. I actually want to walk to the previous one because I'm resetting the next pointer on it. Okay, so our rover points to here, and then I have a whole bunch of items that I wanted to add in. Let's go back to this type of situation before I had added that in there. Rover points to here, and I want to insert. So what I can do, if I were just inserting one element, I make the new element and I make it point to here, and then I change rovers next. Okay. That would be simple enough to do. But now I want to be able to repeat this again and again, to insert something after this one, and then after that, and after that. Well, it turns out if I take rover after I make a new node, set rover to be here, and then repeat the same process over and over again, I will get the results that I want. So my rover is on the node before where I'm inserting, and then I want to have a for loop that is going to pull each element off of elements. And for each one of these elements, I want to make a new node. So rover.next equals new node of that data element and point to rover.next. So once again, because it has to do the right side first, that builds a new node and points to here. And then after it's done building that node, it makes the pointer go to the new node. Once I have that, rover equals rover.next to advance forward, and then we'd pull off another element and we'd repeat the same process over and over again. Okay, so this seems fairly good, and indeed I think it's reasonable if we're in the situation where we're adding into the middle of our list. What if we're adding at the beginning or the end? Well, if we're adding at the end, we'll know that because when we're done, rover, which points to the last thing that we added, if rover.next is null, well then if any node that has a null as its next pointer is the tail. So we should update tail to reflect that. What if we're adding at the beginning? Well, if we're adding at the beginning, all of these things originally were supposed to change the, well, our first node was not supposed to be a rover next here. It was supposed to be head. Okay, so, yeah. And rover is supposed to point to the thing before this. I could try to put in some complex logic in here that would make it so this one loop would do what we want, but I'm not going to. To me that seems more error prone, and so if in is equal to 0, then I'm going to do some special case logic. If n is not equal to 0, then I'll do what we have down here. When n is equal to 0, I'm actually going to do things somewhat similarly. The first thing I'm going to do is I am going to make a new node and make for the first element. I wonder if we can make the assumption there are elements. Probably not. It's possible that elements could be empty, in which case this doesn't add anything. Hey, on that, num elements plus equals 1. Let's make sure that every time we add something we increment our num elements. Otherwise, things get ugly. Okay, so what I'd like to do here, all of my adding winds up working pretty much the same way, except for the first one. Okay, the first one has to be handled differently because I'm not setting a rover next, I'm setting it to the head. And this is a traversable, so we can go across it multiple times. And I actually want something that's going to be consumed here. Okay. How about HD equals no? If if elements dot non-empty. Okay, I just don't want to have to deal with the case where if elements is empty, and then I can't pull off the first element, yada yada. Okay, so if it's non-empty, then I can call head on it, and everything is happy. HD equals new node of elements dot head, comma, HD. Okay, so I'm linking in a node at the very beginning. I create a, so if we had been in this situation here, I make a new node, it links into there, and then I'm setting that to be my head pointer. Yeah. After that, turns out everything else that I can do can follow the general approach that we had here, where I can create a rover that's equal to that head pointer. So after we've added our first one and we're in this situation, I'm going to make rover point to right here, and the next thing I pull off of elms should go after that. So I'm going to copy that code down. One minor difference: I don't want to run through all of the elements because I just put on the first one, so I'm only going to run through the tail. My rover is equal to that first element, so rover.next equals the new node. Make sure that we increment the elements in both those locations. Rover equals rover.next. So run, and apply them all. If when we're done, the last thing that we added has a next of null, it's also our tail. Okay, and so this will reset the head. What happens if we call this and we give it an index of 0 and our entire list was empty? Let's make sure that that boundary case is correct. Well, it will pass through here because it is not it's not less than 0 and it's not greater than num elms. It's equal to num elms, and it's equal to 0. And if the stuff that we're adding is non-empty, then it comes into here. So it takes and sets the head equal to this new node for the first element off of elms. Now note that tail is still like completely null at this point, but we've added one element in and we've added to our counter. And then we set rover to point to that first element that we added. We pull off the next thing that we're adding, we make a node, and we link it in. Count it, and move on. When we're done, because in this case, if the entire thing was empty, rover's next. Every single one of these times when we're setting this right here, this will always be null because the head had been null. So this first pointer got a pointer to null there, and then that is the rover the first time through, and so this becomes null, and then it becomes null, boom, boom, boom. That null just gets pushed further and further back. So when we're done, we find, hey, there is a null, and we set this equal to the tail. Okay, so this is a complete implementation of our singly linked list, the mutable singly linked list. It's not exactly short, but it's not heinously long. This needs to be tested. Okay, there's definitely sufficient complexity in here that we need to write unit tests for this and make sure that it works and does what we want to. But that's not going to happen in this video. So we'll see you again later.